previous lecture we were discussing about the weighted residual method and its basic understanding. Next let us take the second example where we consider a method called as point collocation method. So, point collocation method, what we do? We try to have the weighting function as a special function. So, we do not go through this route. We have the weighting function as the Dirac delta function at some chosen points which are collocation points. What is the whole idea? The whole idea is that you try to satisfy the value of the function at some chosen points given by x equal to xi. So, this is the delta function. So, when you have this one, then what is the result of the integral? So, you have integral r w dx equal to 0. So, what is r? R is, so it depends on again that what is your trial function. Let us say we keep the trial function same. This is the different method, but it does not mean that we have to forcefully choose a different trial function. We can keep the same trial function. We have understood one thing, how this method is different, choice of the weighting function is different. So, different methods are basically formulated based on different philosophies by which the weighting functions are formulated. Of course, you can have different trial functions, but that is not a necessity, but as you go from one method to the other, these are all special cases of the weighted residual method. You have to consider the concept of the weighting function in a somewhat different way. So, when you have this one, so basically what it becomes, r at x equal to xi is equal to 0. So, if there are many such points, collocation points, then it will be a summation of that. So, but here we consider only one collocation point. So, point collocation method, in this example we consider only one collocation point. Again this is an example, say x equal to 5. So, collocation point is a point where you make the function satisfy its requirement, that means at that point the error is exactly equal to 0. We are, this is the ideal thing, in general we are trying to minimize the error, minimize the sum of the residuals in some weighted sense, but here in the collocation method you are only focusing your attention on some specific points and trying to make sure that the corresponding errors are 0. So, at x equal to 5 you are considering only one collocation point. Here if you consider multiple collocation points, it will be sum of the residuals at those collocation points, but here you consider only one collocation point. So, r at x equal to 5 has to be equal to 0. So, that means you have minus 2a plus 100, here r is such a function which is not a function of x. So, it does not matter what is the choice of your collocation point, but that is because of this very special simple example, otherwise r could itself depend on x. So, minus 2a plus 100 equal to 0, that means a equal to 50. So, this has given the same solution. The third example, example 3, we consider as Galerkin's method. In the Galerkin's method, So, we have seen in the previous methods, previous two methods we have chosen the weighting function in some special way. Galerkin's method also does it in a very special way. It considers the weighting function same as the trial function. So, it considers same form of the two functions, so that your sort of degree of freedom is somewhat reduced in terms of choosing the weighting function. Once you choose the trial function, you have automatically chosen the weighting function, you can't choose it anything beyond the form of the trial function. So, if you want to see that how that can be implemented, let us consider the same y approximate. So, the weighting function, remember the weighting function we consider without the parameters. So, we take weighting function we consider as x into 10 minus x, we do not consider a as a part of the weighting function, because it is the weighting function equal to trial function in the sense of the form. It's, if you just keep the form, that is sufficient, because a is just a constant multiplier. So, if you multiply it with multiply the function with ax into 10 minus x, it is as good as multiplying it with x into 10 minus x, because integral of r w dx equal to 0. So, if you put a or if you do not put a, it does not matter, because eventually a is not equal to 0. So, just for simplicity we just, but if you are interested to write it in the full form, you can write it a, but we are not writing it a here, because eventually it is the form of the weighting function that matters. So, let us now do this exercise. So, integral of, if you choose the same approximating function minus 2a plus 100 into x into 10 minus x dx equal to 0. So, what should be the value of a? A will be 50, because the remaining part of the integration, if you take this out of the integral, remaining is just a number. Integral of x into 10 minus x dx from 0 to 10 will be just a number. So, that means effectively minus 2a plus 100 will be equal to 0, that is a equal to 50. Now, we have seen 3 examples, and in all these 3 examples we have come through the roots of the weighted residual technique, which has some resemblance with the V form or the variational formulation. Now, remember that we had different forms of the governing equation. We had the original form as the differential form or the D form, we could reduce it to a V form, and subsequently we could also reduce it to a M form or the minimization form. So, let us see that whether we can tackle the same problem by utilizing the concept of the M form, again using some approximating function, but not using this form, but using the M form. So, let us see that how we go through the roots of the M form. So, before doing that, one important thing that we should keep in mind, that no matter whether it is the least square method or the point collocation method or the Galerkin's method, that these are not the only methods, these are just some examples that we have considered. You could have different other methods where you may choose different forms of the trial functions, like there is a very commonly used method called a spectral method. In spectral method, what one does is one uses the truncated form of an infinite series as a trial solution. So, you could have some special polynomial functions or special functions which are of forms of the infinite series, and in the special functions of the form of the infinite series you truncate it up to a finite number of terms, and that you call as a spectral method, so to say. So, we are not going into all those methods, but these are just to illustrate that how you can make a weighted residual formulation given the philosophy of a method. Now, the M formulation also is similar. We could have several types of methods derived from the M formulation, but we will consider only one type of example. But before that, let us derive the M form of the equation. So, we have done it a similar case earlier, so let us do it quickly. So, to derive the M form we first derive the V form. So, we integrate it with respect to x by multiplying it with V and set it to 0. So, then what we do, we integrate it by parts. So, V into dy dx minus integral of dv dx into dy dx equal to 0. So, you have come up with a boundary term V into dy dx. Now, let us try to answer some questions. What is the variable on which you are giving the essential boundary condition? It is y, because V is variation of y, variation in y. So, that is called as the primary variable. Primary variable is the variable on which you are giving the variation in the boundary term. So, you have two types of variables, one is primary variable, another is secondary variable. Primary variable is this one, I mean if this is delta y, then this y is the primary variable, not V. And secondary variable is dy dx. Specifying the primary variable at the boundary is essential boundary condition, specifying the secondary variable at the boundary is natural boundary condition. Here both the boundary conditions are essential boundary conditions. So, that means you have V equal to 0 at both x equal to 0 and x equal to 10. So, this term is no more important, becomes 0. So, once this term becomes 0, you are left with integral of dy dx dv dx between 0 to 10 is equal to integral of 100 v dx. This is of the form a y v is equal to L v, where A is a bilinear operator and L is a linear operator. So, this is A and this is L. What are the requirements that these are satisfying? These are continuous functions. Not only that, a y v equal to a v y. So, A is symmetric and A is bilinear, because in place of y if you substitute alpha 1 y plus alpha 2 v, and in place of v you substitute beta 1 y plus beta 2 v, then you can see that you can expand it in the form of functions which are individually linear in each slot. We have seen that what do we mean by a bilinear operator, and here it satisfies that. Similarly, this L is a linear operator. So, in place of v you can substitute say alpha y plus beta v, and you can see that it is alpha into L of y plus beta into L of v. So, that is a linear operator, but is it sufficient to derive the M form on the basis of symmetry and bilinearity and linearity, or you require something else, you require additionally that it must be a positive definite operator, that means AYY must be greater than 0, and that is indeed the case, because if you AYY means you replace V with Y. So, it becomes dy dx whole square dx, integral of dy dx whole square dx is greater than 0, because dy dx whole square is positive and the domain of the integration is also 0 to 10. So, you have AYY greater than 0, that means it is positive definite operator. So, that means its M form exists. So, M form is, what is the M form? Minimize pi equal to half AYY minus LY. We have derived it earlier in one of our previous lectures. It is very easy to derive it straight away from here by substituting V equal to delta Y, and it will come out to be delta of this pi equal to 0, that means minimize pi. So, that means minimize half integral of dy dx whole square dx minus 100 y dx. Now, if you approximate, so use an approximate function in place of y and minimize pi, then that is one way in which you can achieve this minimization through an approximating function. So, here also you are having a trial function, but what is the difference with the other methods like the Galerkin's method? You do not have any weighting function here, you have just a trial function and you do not require any weighting function, but you had to pay a price, or rather you had to have a requirement satisfied because of which you can do it, that it is a positive definite operator. If it were not a positive definite operator, you could not have been able to come to this form. So, here you have come to a form where it is not only a minimization problem, where you require only a trial function, not a weight function, and also the continuity of the trial function is one order less than that of the ordinary differential equation originally given.
That is pi equals to
Half a yy, yes, this is half a yy. So, now you try to minimize this one and set its derivative with respect to a equal to 0. So, you can see that you can do that. So, we are considering y approximation, y approximate same as a into x into 10 minus x, the same form. So, your objective is to minimize this based on the choice of this approximating function. Your approximating function, it could be up to continuous up to first order derivative for this case. Here of course it is continuous up to second order derivative, that was very much essential for the weighted residual methods that we have used. Why? Because there we could not utilize, or rather there you did not utilize the integration by parts and the related reduction in the order of the continuity requirement. Here you have already utilized integration by parts, so the continuity requirement is one order less. Similar thing you can do for a fourth order equation, then you can come up with up to second order derivative. So, you can reduce, you can use functions, approximating functions with reduced requirement of continuity, and no weighting function is necessary. So, that is one of the advantages of this method, and this method is known as Rayleigh-Reed's method. So, let us do this exercise integral of. So, what in place of dy dx we will be approximating it with dy approximate dx. So, then pi will be half of dy approximating dx whole square minus 100 y dx. Minus, here also y is y approximate, in place of y approximate a x into 10 minus x dx. So, let us complete this one. So, the remaining part is simple algebra. If you help me, then we can do it a bit quickly. There will be one a square, then 10 minus 2x whole square dx, 0 to 10 minus 100 a So, you have del pi del a equal to 0, that means which implies a is equal to okay. So, you can complete this exercise. This is a very simple exercise, and at the end if you do the integrations, there is no surprise, here also you should get a equal to 50. Question is why we have got a equal to 50 for all cases. So, it is very easy to come to that conclusion. For that you just complete the analytical solution of this equation. So, you integrate it once, dy dx is equal to minus 100x plus c1 and y is equal to minus 100 x square by 2 plus c1 x plus C2. So, apply the boundary conditions at x equal to 0, y equal to 0, that means C2 equal to 0. Second boundary condition at x equal to 10, y equal to 0. So, you can cancel one 10 here. So, C1 is 500. So, y becomes minus 50, sorry, if you take 50 as common, then 10x minus x square. So, 50x into 10 minus x. You can see that this is a special case where the approximate solutions and the exact solution are the same. This is the exact solution. The reason is that the exact solution is itself a second order polynomial form, and we have chosen the trial function also to be a second order polynomial form. So, we have used 4 methods actually, and in all the 4 examples we have used the same trial function, which is the second order polynomial function. Our objective was that what is the unknown coefficient in that trial function, so that the error is minimized in some way. In 3 of the cases we have gone through the route of the weighted residual method, in another case we have gone through the route of the Rayleigh-Ritz method, but whatever was the method, the objective was to minimize the error based on a particular choice of the trial function, and that choice of the trial function happens to be the exact form, and therefore what you can see here is that this coefficient 50 is coming out to be same no matter whether you are using the actual exact solution or the approximate solution. In reality that will not happen for a problem, because you do not know what is your exact solution. So, your exact solution form will always be different in reality than your approximating function form. Only in an accidental case or where you know the solution and you are just going for a check, in such cases it may be same, but in general not. So, what we have learnt out of this? We have learnt that how to use the M form or the V form to get a corresponding approximate solution of the differential equation. But one important thing is that these approximate solutions are global in nature. That means if you have the domain like this, you have an approximating function which you intend to make to be made valid over this entire domain. So, you have this y approximate as ax into 10 minus x, that is a global form of the function that you approximate for as a solution over the entire domain. However, what you could do to improve upon your solution, you could use a higher order polynomial. Here it is not necessary, but there are some problems, or in fact for most of the problems your accuracy of the solution will go up if you use a higher order polynomial, but higher order polynomial will mean more calculations and more tedious calculations. So, how you can reduce those calculations in a way, in a more effective way? You consider the domain to be locally divided into number of subdomains, and you consider lower order polynomials for approximating solutions over each of these subdomains. So, what you are doing is you are now not considering a global solution, but a local solution. Because you are considering a local solution, your entire global solution, it may be whatever, very complicated, but when you consider a small part of the domain, then this may be fitted by lower order functions. Whereas, if you wanted to do it in one shot over the entire domain, you would have required a much higher order polynomial function. So, you are reducing the requirement of the order of your polynomial function, but the cost that you have to pay now is that now you are sort of dividing your domain into a discrete number of subdomains, and for each subdomain you are going for a lower order polynomial to approximate your solution. That is the advantage, but the limitation now is that you are no more having a continuous variation, but you are having only discrete points and your solution is fitted within these discrete points. So, this is the basic concept of discretization. So, let us sum it up, that what is discretization? Divide the domain into numbers of discrete subdomains. The names of these subdomains may be element, control volume, depending on the particular method that you are choosing. So, once you divide the domain into a number of subdomains, then each subdomain is represented by a discrete set of points. So, the continuous variation of the function is lost. These discrete sets of points, these are called as grid points or nodes, depending on again the method that you have chosen. And then your objective is to convert the governing differential equation into a system of algebraic equations valid at each of these discrete points. That is the task of the method itself. So, we can see that you can have different methods in principle. You can have, for example, we will see finite difference method, finite element method, finite volume method, that we will see in our subsequent lectures. But first and foremost, it is important to appreciate the general philosophy of this method. So, what you are doing? You are losing the continuous nature of the solution and considering the solution to be obtained for a discrete set of subdomains or points, and for each of these points you are tending to write a system of algebraic equations. Your objective is to convert the ordinary differential equation or partial differential equation, whatever, into a system of algebraic equations, and there you apply the particular method that you are intending. It could be finite element, finite difference or finite volume. How we can do that? That is where the heart and soul of the computational fluid dynamics lies, and that we will take up in our subsequent lectures. Thank you.